So this lecture is going to focus on Faraday's law, and we want to draw some conclusions from some observations that have been seen to be true. Now, the basic message behind Faraday's law is this, or the basic message of Faraday's law, I should say. Imagine I have a coil of wire, and that coil of wire is connected to an ammeter, and I have a magnet like this. It's got a north pole and a south pole. And the magnetic field lines are going to do something like this. Okay. My drawing is not all that great, but actually, as a matter of fact, you know what? Let's go ahead and actually get rid of that. Let's redraw that. And let's say that this is the North Pole. Let's say this is the South Pole. And if that's the case, I'm going to try to draw these field lines a little bit better, and we'll draw the field lines in green. So imagine I have one field line that looks kind of like this, and another field line that looks like this, right? And remember, these field lines, the shapes of these field lines do not indicate their strength, right? The field lines closer to the magnet are going to be stronger. But the idea is that some of these field lines are going to penetrate into the cross-sectional area of the loop. Let's call that A. Okay. And what was noticed is if I brought this magnet close to the loop, right? So I bring the magnet in and I bring it close to the loop, the ammeter sees a tick. And if I take the magnet away, the ammeter sees another tick. But these ticks are opposite in sign. The current will flow one direction when you push the magnet toward the coil, and it'll move in the opposite direction when you pull the magnet back. And then when the magnet is stationary and or essentially the magnetic field lines are not really strong enough to be moving through the coil, under those two conditions, you don't see any current. Number one for a stationary magnet, or number two for a far magnet, right? Oop, not magent, but magnet. Um, and so what we have observed, oh, and by the way, okay, all else being equal, if your wires are ideal, the larger your area, means bigger blasts of current. Okay, so the larger your area, the more your burst of current is going to be. And so all of these observations put together lead to the idea of what is called electromotive force. Or EMF for short. Okay. Now, electromotive force was coined before we really realized what voltage was and how current was flowing through the wires and what current was, those types of things. But it has historically stuck. Okay, so electromotive force is essentially voltage, right? But we use the symbol epsilon for electromotive force to differentiate it from a DC or direct current source like a battery. Okay, but just know that electromotive force is effectively a source of voltage. Okay, so electromotive force is a source of voltage. So what this means is if I put a resistor in here, okay, if I put a resistor in here, then I can predict what the value of the current will be if I know what the EMF is going to be. Okay, so Ohm's law would hold. But again, the current is not constant, it is a burst of current. And you notice that the current changes when the magnet is pushed toward the coil or the magnet is pushed away from the coil, or the magnitude of the current changes when you change your area. Well, we've already seen a concept like this when we talked about the electric flux, which was equal to the integral of the electric field over a area, right? So this was the electric flux, and we defined the magnetic flux to be the same kind of thing. It's the strength of the magnetic field. Now, the electric flux was actually over a surface, right? But that surface has an area, and the magnetic flux is the cross-sectional area of a loop or a plane or something like that. It doesn't necessarily have to be a closed surface. With electric flux, it had to be a closed surface because charges come in individual points or monopoles, whereas magnets don't do that. So we don't have to worry about whether or not our surface is closed. And as a matter of fact, um, when I take uh, the electric flux was actually over a closed surface, and the magnetic flux over a closed surface is automatically going to be zero. And we'll talk about that in a little bit more detail in a future video. But for now, the magnetic flux is the integral of the strength of the magnetic field piercing an area, and you integrate the dot product over the entire area. Okay, now for simple systems like a loop, if I just have a loop of wire and my loop is a circle and it has a radius r, okay, and I have magnetic field lines from somewhere, I don't care where, penetrating through that loop, and let's just say that this is a uniform magnetic field for the moment, right? Then the flux magnetic flux is just going to be the strength of the magnetic field times the area, or dotted into the area. But the area of the circle is going to have the same direction as the magnetic field in this case, or they will be oppositely oriented. It doesn't matter because it would change the sign, but the sign in this particular case is arbitrary, and we'll talk about why. But for the moment, it's just a matter that your surface area is directionally pointed parallel with your magnetic field. And so when that's the case, the integration over the area just becomes the total area. So the flux in this particular case is just going to be B dot A, right? But if we come back up here, we're not interested in just the flux. We're interested in why there is a current when I move the magnet or when I move the coil or when I change the size of the coil. So what this implies is that when I move the magnet, okay, when I move the magnet or when I change the size of the coil or when I change the position of the coil, any one of those, what I'm doing is I'm changing the amount of flux with respect to time. So what Faraday concluded is that the voltage induced in the coil that then allows the ammeter to make a measurement, that EMF that's induced is going to be proportional, let me draw the proportional sign, to the change in the flux with respect to time. Okay? So the electromotive force is going to be proportional to how the flux changes with respect to time. If I have a static flux, I don't see any current. That's why if I don't move the magnet and I don't change the coil, if everything is static, I don't see any current. When I move the magnet or when I change the coil or both, then I will see a current. Right? Now, it turns out we're going to put a negative sign here. So formally, this is going to be dB dt, or d phi dt rather, with the negative sign. The negative sign will play a very important role in determining what direction the current is flowing, and this is known as Lenz's law. And this is known as Faraday's law. Okay? So if I know the rate at which current is changing, I can predict, or not the current, but if I can measure the rate at which my flux is changing, I will be able to calculate the voltage induced. And if I know the resistance, then I can use Ohm's law to get the current. So to make an explicit example, right? Let's make an explicit example. Let's say that we have a loop that is 0.5 meters in diameter, okay, or in radius rather. And we've got some magnetic field piercing through here. And let's say that the magnetic field is dependent on time. So the magnetic field is a function of time, and let's just give this a value of 1 Tesla. And as a matter of fact, let me write this over this way just a little bit. So my function of time is going to be 1 Teslas times e to the negative 0.25 times time. So my negative 0.25 is going to have units of 1 over seconds. Okay. And if I want to make that a little bit clearer, I might write it like this. Okay. So this is an exponentially decaying function, right? This is an exponentially decaying function. Um, and at time zero, the magnetic field will have the value of 1 Tesla, right? At t equals 0, the magnetic field will have the value of 1 Tesla. And the flux is going to be written as B dot A because I don't need to integrate over a circle. I already know what the area of a circle is. It's 2 pi, I'm sorry, pi r squared. So I can already assume the integration is done. And this is going to be pi r squared and to keep everything in symbolic form, I'm going to label this coefficient, this 1 Tesla coefficient, as B naught, right? So this is going to be pi r squared B naught e to the negative 0.5t, or 0.25t. Okay. Now I'm dropping the units on the 0.25. I'm assuming that we all understand it's 1 over seconds. It has to be 1 over seconds. Why? Because your exponential function has to be unitless, so these two units have to cancel out. So this is just a number, right? The 0.25 just indicates the rate at which this is going to decay. Okay, this is just going to indicate the rate at which this is going to decay. So here are my questions. Number one, if this function or if this situation is true and my magnetic field is a function of time, it's decaying, it's constantly changing. If it's changing, it will produce an EMF. So I want to know what the EMF is. And by the way, your EMF does not need to be constant. It can also be a function of time. Okay. Um, so what is the EMF? And two, or B rather, I want to know um, at what time at what value of time is B equal to 1/2 B naught? Okay. So these are the two questions I want to answer. And by the way, because your area is not changing, what this question part B is effectively the answer to it would also tell you is when the EMF also has dropped by a factor of 1/2. So whatever the initial EMF would be, since my magnetic field is decaying, eventually the magnetic field will decay down to 0, practically 0, and it will become static and my EMF will die off. So we would expect the EMF to also be an exponentially decaying number or value. And therefore, the current is also going to be exponentially decaying. Okay. So, what is E, and at what time does the magnetic field drop off by a factor of 2? So, let's work these out. And for A, we find E by taking the negative d phi dt, okay? And this is going to be the same thing. If I want to write it in terms of A and B first, this would be negative dB dt times A plus dA dt times B, just the product rule. But if my area is not changing, then this part goes away, and this is just going to be A times dB dt with the negative sign. And so this is going to be A, we said, is pi r squared. B naught is just a constant. So now I get to the sign here. So this is going to be negative 0.25 times e to the negative 0.25 times t. Okay? And I need to put that there. So I've got these two negative signs. They're going to cancel out. And my EMF is going to be described as B naught pi r squared times 0.25 times e to the negative 0.25 t. So it's still an exponentially decaying function, but this is indicating that our initial EMF, this is EMF naught, okay? Our initial EMF is going to be positive, and then it's going to decay, okay? That's what this is telling us. And you can plug in the numbers, right? If I were to give you something like this, you could plug in the numbers, and come up with a number for any question I could ask. But what about part B, right? So for part B, if B is equal to B naught e to the negative 0.25 t, and I want to know what t is, when b is equal to half its original value, then this would be 1 half b naught is equal to b naught e to the negative 0.25t, and my b naughts cancel out. I'm left with 1 half is equal to e to the negative 0.25t, and so then I've got the natural log of 1 half is equal to negative 0.25t. And the natural log of 1 half is the same thing as the natural log of negative 2 equals negative 0.25t. My negative signs, log of 1 half is equal to the negative log of 2, not the log of negative 2. You can't take the log of negative 2. It's negative the log of 2. And my negative signs cancel out. And so then t is, which needs to be positive, which is a good thing. T is going to be the ln of 2 divided by 0.25, or the same thing as 4 times natural log of 2. Okay? So this is how long it takes for the magnetic field to be dropped by a factor of 1 half. The natural log of 2 is like 0.693 and some odd stuff. So if we round that up to 0.6 or a 0.7, 0.7 times 4 is what, 2.8. So this is approximately 2.8 seconds for the system to drop off by a half in the strength of the magnetic field. But notice, right, if we come back up here, the expression for E, or the EMF, and if I group my magnetic field terms together here like this, you'll notice this is the quantity that appears here, right? So since that's the only quantity that's changing, my area is not changing. This is also the time for which the electromotive force will have dropped by 1 half its initial value, all right? So if I had an ammeter hooked up in this circuit, I would just watch my ammeter plummet, right? I would just watch my ammeter drop. After 2.8 seconds, it would drop by a factor of 2. After another 2.8 seconds, it would drop by a factor of 4. After another 2.8 seconds, it would drop by a factor of 8, and so on. Okay. Um, Now, back to this negative sign. Okay, what does this negative sign mean? So, this is Lenz's law, and Lenz's law is summed up by the phrase nature hates change. So, what's happening? When I have a situation like this, okay, and my magnetic field is going to die down, I'm going to induce an EMF in my coil, and that is going to cause a current. The current is going to induce its own magnetic field. We've already seen that. We've already seen how to calculate the magnetic field of a loop of current carrying wire. Lenz's law, or the idea that nature hates change, basically says that the induced current is going to be in such a direction as to try and stop the flux from changing. So, whatever the original flux is, that's what Mother Nature wants the system to stay at. So, it will induce a current to try and compensate for the change in the magnetic field. So, in the case of the loop that we have here, okay, in the case of the loop that we have here, what this is effectively saying is this: if I have my loop in two different configurations, okay, two different times, one time with the magnetic field very strong, let's call this time 0, and then at time t1, the magnetic field in our example has dropped by a factor of about half at a time of 2.8 seconds. Okay, so my magnetic field has gotten weaker. What Lenz's law says is that nature hates change, so the induced magnetic field inside the wire is going to try and counteract that loss. So it's going to try and produce its own magnetic field to make up for that loss. Okay? It's going to try and make up that loss. It won't be able to do it completely, but it tries, right? And so as a result, we can then specify the direction of current if we know the direction of the magnetic field. So the R is the induced magnetic field by the coil's current itself. Okay, the induced magnetic field by the coil. And that means that if I use the right hand rule for currents and magnetism, then I can say what direction my current is going to flow. If I need my current, or if I need my magnetic field to be upward through the loop, then my current will have to flow this direction via the right hand rule. Okay, so my current is going to flow this direction. If the change in flux were positive, like if the magnetic field was growing, then the induced magnetic field would seek to offset that, and my arrows would be pointing downward, and my current would be reversed. Okay, so that is the issue of Lenz's law. But this is Faraday's law. Okay, and there are a host of consequences with it and a host of interesting examples. But I hope that this gives you a introduction to the basics of it and why the negative sign is there and how to do a little bit of calculation with it. And we will extend this with a few more examples in the next video. So we will see you then.